we're going to see how easy it is to change the pH of water using more or less everyday items, and explaining what's going on along the way. To lower the pH, we're going to try carbonated water. It's basically water with a lot of CO2. And muriatic acid or hydrochloric acid, maybe not your everyday item, but I want to try something stronger. This can be used to clean steel or change the pH of soil, and I don't recommend playing with this at all. To increase the pH, we're going to try seashells, basically calcium carbonate, and caustic soda or sodium hydroxide, a major component in drain cleaners, and again, super strong, and I don't recommend using it without proper guidance. We have seen before that pH is a property of anything with water. Among water molecules, we will always find a small fraction of hydrogen ions and hydroxide ions, and pH represents how many of each there are, using a simple number. When these ions are perfectly balanced, water has a pH value of 7. But when one of these ions starts taking over, the pH value will change. Either hydrogen ions will blow up in numbers and the pH value goes down, or hydroxide ions will dominate and the pH value goes up. This pH scale covers all these possibilities, with the columns representing the amounts of these ions. This is a simplified version though. The actual version will look like this, with each column being 10 times larger or smaller than the next. Technically, it's possible to get a pH value even below 0 and above 14. I have purposely simplified so that it can fit in the screen. Our water here has a pH close to 7, more like 6.6. The point is, we can change this by breaking this proportion. We do this by adding something with a more extreme pH value, an acid or a base. By adding an acid, we will increase the number of hydrogen ions. These will stay in solution, but also a bunch of them will target hydroxide ions and get neutralized, forming water actually. All of this takes us down in the pH scale. This is what muriatic acid will do in water. Its molecular formula shows a hydrogen ready to detach and do its thing. Carbonated water is similar, but first the dissolved CO2 reacts with the new water to form carbonic acid. And now it's ready to set loose a hydrogen ion. All of this happens very quickly. Let's start our first test with carbonated water. When we add 1 milliliter of our carbonated drink to half a liter of our water, we see a change in pH as soon as we mix, from 6.6 down to 5.32. Another milliliter will further drop the pH, but only to 5.12. Another milliliter, and we barely get under 5. You see, the drop in pH won't be linear. As we move away from a pH of 7, it's like our acid loses its effect, and we need to add more of it to further go down. This is because pH is not linear. Our second test is using muriatic acid. If instead we start with 1 milliliter of muriatic acid, the pH drops from 6.6 all the way down to 1.7. The difference between both acids is due to their different strengths. Carbonated water has a pH of 4, and our 30% muriatic acid should have a pH close to 0. This means a milliliter of muriatic acid has easily about 10,000 times more hydrogen ions than our carbonated water. Let's move on to our bases now. Seashells and caustic soda. We have them in solid form, so first we're going to make them liquid. We will prepare a caustic soda solution 30% by adding roughly 41 grams into some water for a final volume of 100 milliliters. And now that this is wet and hot, we need to be extra careful handling it. The shells needed to be crushed by mortar and pestle. This took some time, but after a while we managed to get some fine calcium carbonate, and even leave some bigger chunks for later use. Another thing about calcium carbonate, we cannot dissolve much of it in regular water. I added 0.5 grams in a liter of water, knowing that only about 3% of it would dissolve, while the rest would just settle down. Adding a bit of salt, shaking the bottle several times a day, as well as keeping it cold, should help saturate the water with as much seashell powder as possible. I have my liquid bases. Now, how do they increase the pH? Well, if an acid releases hydrogen ions, we could say a base is something that releases hydroxide ions. Clearly, that's what caustic soda does here. Its molecular formula shows indeed a hydroxide, ready to detach and accumulate in water, but also take on some hydrogen ions and again neutralize them by forming water. An even more accurate way to describe a base is simply that which takes free hydrogen ions away from solution. An acid gives hydrogen ions, a base takes them. The seashells we dissolved dissociated into the ions calcium and carbonate. This carbonate is hungry for hydrogen ions. It has literally compartments ready to pick and hold at least one hydrogen ion. Not only will they collect free hydrogen ions, but they will also steal a hydrogen ion from innocent water molecules, which are now left as hydroxide ions. So this has finally the same effect as caustic soda. They both take hydrogen ions and they both increase hydroxide ions in their own way, taking us up in the pH scale. Let's put this to the test, starting with our seashell water. For some reason, adding 1 milliliter of seashell water did not increase the pH right away. I kept adding another milliliter and another, and if anything, the pH went down. Very confused, I checked the seashell water and its pH was over 9.9, which is fine. Maybe I should have waited just a bit longer. But desperate, I kept adding more, and it wasn't until I added 25 milliliters that I started seeing a proper increase. After yet another 25 milliliters of this seashell water, the pH finally stays at 8.6. But I'm left wondering about what just happened. Let's redo this test with caustic soda. When we add 1 milliliter of our caustic soda solution, the pH goes all the way up to about 12.2. Big difference. Just like muriatic acid was the strongest of the acids, caustic soda was the strongest base. We can make the pH go up and down much more easily with these compounds. It is especially easy to change the pH values around the middle of the scale. The lack of ions here makes this part of the scale very sensitive to what we add. As far as our carbonated drink and seashell water go, they will have their limitations. We can still move the pH up and down, but in a much narrower range. However, if we just keep adding these two compounds back and forth, we are secretly building an army of carbon molecules. Both carbon dioxide and carbonate are forming the same ion when reacting in water, bicarbonate. And this army of carbon molecules are now making it harder to change the pH. Even if we go back to our strongest acids and bases, now it takes a lot more to move the pH anywhere in the scale, even through the middle values, which is great if we want to have a stable pH value at around 7. If you have heard of the terms carbonate buffer system or alkalinity, they have to do with this stability, and this deserves its own video.